Let's get started. So in the last class we looked at the Reynolds stress equations, and the equations were also not closed. It had far too many unknowns, alright, and so therefore there is no point continuing in that direction, that is again trying to get an equation for a triple velocity correlation and so on. More and more you go in that direction, more unknowns come, so that equations always remain not closed. Therefore modeling is the right direction for that. So before we visit the modeling part, of course we need to first understand each of these terms, right. I mentioned that there are particularly 4 terms on the right hand side: the rate at which the production occurs of Reynolds stresses, rate at which it diffuses or transports due to pressure, due to viscosity and due to turbulence itself, and also the rate at which it gets destroyed or dissipates, and the rate at which it redistributes, where turbulence is redistributing. We will see what that, we will get started with that part, the redistribution. So before that I would like to introduce some concepts in the statistical analysis, because we will kind of take help from a flow problem to understand its behavior. So let us revisit the statistical analysis. So one, I just call it revisit statistical analysis. Okay. So in this I would like to introduce 2 new concepts to you. One is called what is called a statistical stationarity. Okay. Statistical stationarity. So what this means is, when we say the flow is statistically stationary, so we have to understand I am not talking about a stationary flow. Turbulent flows are not stationary flows, right. The turbulent eddies or vortices are always moving around. So turbulence, we already defined, is a 3-dimensional unsteady process. Okay. So flow is, a turbulent flow is not stationary. So I am talking about statistical stationarity. Okay. A flow where it comes to a stage where it is statistically stationary. This is important for, especially when you do experiments or if you are doing the simulations, then you need to know from where I need to start to take my measurements, from where I should start to record the data for that part. So what it means is, if I explain to you as if we are doing some simulation or experiment, is, let's take, you have a flow. Okay. So let's say there is a flow here between 2 parallel plates. Okay. So let's say this top plate is moving to the right direction, the bottom plate is fixed. Top plate is moving to the right direction. Are you familiar with this type of a flow? What is it called? A coed flow. Okay. This is a plane coed flow. You also get a Taylor coed flow or a circular coed flow, that is the flow between 2 concentric cylinders, okay, rotating in relative motion. So this is a plane coed flow. This is just an example, it can be applied to any flow. Just take an example, a plane coed flow, turbulent of course. So in this particular flow problem, so the top plate moves to the right in relative motion to the bottom one, which is fixed. So you get some turbulent motion in between. So let's say you are going to record a data at, let's say, at this position. Okay. Let's say a student X wants to record data at this position. Okay, x1, y1, z1, x1, y1, z1, t at a particular t. Now for some reason he gets sick and he cannot continue the experiment, but today he has recorded the data, and he will come back and he will take data again, okay, at the same location. If these 2 statistics are matching, then what does that mean? He has taken many samples and he has done the statistical analysis. He has calculated the mean velocity, RMS, all these things, all the statistics that we discussed, variance, standard deviation, third order statistics, all this. He has done all the statistics by measuring data at a certain location x1, y1, z1. So this student, let's call A, has done the measurement, and then he has come back another time, maybe the same day or the next day, and he gets new data. Let's say the tunnel is still working. Let's say this is a wind tunnel experiment where it is still working, and he will come back and measure. If he is going to get the same statistical data, that means the flow has come to a statistical stationarity. The statistics are not changing in time. Okay, so statistics are independent of origin in time. Statistics are independent of origin in time. That means at what time t you started doesn't matter anymore. Okay, so this can be illustrated. For example, if I just take the same case and see how the data would have looked. So let's say I am plotting a graph here, okay, where I am looking into, let's say, u1 velocity. That student A is taking many samples. So the flow, let's say, goes from, in the beginning there is no flow, he starts the blower, okay, he starts the wind tunnel, and the flow starts to come, and then it will go, and then it starts to go like this, let's say, okay, oscillating. Can you see oscillations, or it looks like a straight line? Okay, so maybe I'll make it more oscillating. Okay, let it stay, it goes up, and then okay, so let's say he starts to get data like this. Now he has taken data, the student is smart, so he will look at this data and decides to remove this transients. Obviously you should not use all this initial part to compute your statistics. So he will decide to take from this particular time instant, let's say, and to up to here, and he gets some average, let's say u1 average taken from, we can make it t here instead of samples, we can make it as time itself. So this is between t1 to t2, he has taken all the samples here is time average to get u1 bar. Now he comes back later and then takes data at another position. It doesn't matter, like, I mean, he can continue to take data here, or another student can come, it doesn't matter. Maybe he will tell his friend, you continue, I am sick. So that the student continues from t2, and then he will take data up to t3, and then he will take u1 bar, he computes it. Okay, so if these two matches, let's call this u1 bar as the sample 1, let's say this is let's call it S1 and this is S2 from two different samples. So if u1 bar S1 is equal to u1 bar S2, both, of course, same number of samples are taken. Let's say both involves 1000 samples, right? The number of samples has to be the same. He is not checking for whether statistics are converging if I increase the number of samples. That is the later part. The first part is to check whether your flow has come to a statistically stationary state, that your statistics is no longer changing in time. If it's come to that part, then this process is called statistics are independent of origin in time. So it doesn't matter when you come to take your measurements, your flow has come to a statistical stationary state, but you need to verify this, okay, before you do any simulation or experiments. Before you take the data to process for statistics, this must be done. Okay. So another concept is, this is clear, statistical stationarity. I am not talking about a stationary flow. Flow is not stationary here. Okay. Turbulence is completely unsteady three-dimensional flow. Yes. Look at the next topic. This is called homogeneity. Okay. Homogeneity, or you can say this is statistical stationarity, the other one is statistical homogeneity, you can say, that is the correct statistical homogeneity. A homogeneous random process. So when you have a statistical homogeneity, what it means is, the same experiment if I take, okay, so the same I have this, I can write in the same place. So now I have so at location x1, y1, z1, let us say both the student A and B are in a hurry to graduate, they want to do simultaneous measurement, okay, they do not have time, they want to do it today at the same time, and the tunnel is very long. So student A decides I measure at x1, y1, z1, and student B decides he will measure at x2, y2, z2, and they will do the same process. Okay, they say, okay, I have got my mean velocity, RMS, all these things. Then they compare. If the statistics from location x1, y1, z1 is matching x2, y2, z2 or any other location, okay, that means as you go in the spatial direction, your statistics are matching. That means the flow has come to a statistical homogeneity. So this is here, of course, it is not x2, y2, z2, let me write, this should be x2, y1, z1, okay, only in x they have moved, but y1, z it is the same position. So here the flow has come to a statistical flow is showing, not come to, the flow is showing that there is a statistical homogeneity in x direction. Every flow need not display this, whether you can get completely inhomogeneous turbulence in all the three directions, but there can be flows where the flow can exhibit a statistical homogeneity in one direction or two directions or all the three directions. Let us say here it is only the x direction where I measure flow at this location and then I measure flow here, and the two mean velocities or URMS or VRMS, any of these quantities are matching between this location and this location or any location as I walk along the x direction. Then I can say the turbulence is homogeneous along x1. So this statistical homogeneity implies that statistics are independent of origin in space, okay. So statistics are independent of origin in space, that is x1 and or x2 and or x3, depends on the flow. For a plane couette flow I can tell that you will get homogeneity both along the x1 direction. Let us say if I going to call this is x1 and if I call this okay, so this is anyway xyz coordinates, so this is x, this is y, and the out of plane is z. So both x and z will exhibit statistical homogeneity in a plane turbulent couette flow. In the y direction you will not, that is obvious, right. In the y or the direction wall normal direction you must get gradients, right. So your statistics, if I measure here, one student will go very close to this wall, the other will go to the close to the other wall, they will measure, okay, that some quantities can become similar. If the profile is symmetric, some quantities but not all quantities, some can exhibit antisymmetric behavior. Okay, so there are gradients exist, so the flow along the y direction for a plane coed flow is inhomogeneous. And we define this mathematically also when I say this statistical homogeneity. So if I say homogeneous in homogeneous, I can say along x1 direction implies dou by dou x1 of all the average quantities is 0. Okay, so this is the bracket term here. So this is just any quantity that you can put here. Let's call it phi. You can put your velocity, standard deviation, any other quantity, any statistical quantity you are looking into. The gradient along x1 should be 0. Similarly for x2, same thing, your dou by dou x2 of, or I can say just dou by dou x2 phi bar equal to 0, and similarly for x3 and so on. Okay, and we can use the same concept also for the statistical stationarity also, because your statistics are no longer changing in time. So the time derivative should be time derivative of what? Instantaneous or the statistical quantity? Statistical quantity. Okay, so here dou by dou t of your, let's say, phi, any quantity has to be 0. Okay, so you should be very clear here. I am not talking about this where phi is instantaneous, or I am not talking about not talking about the random component or the instantaneous which has the random component. I am only talking about the true mean. Okay, dou phi bar by dou t. Similarly here also the same thing. Here also the same thing. Your dou phi by dou x1 is not 0. Dou phi prime by dou x1 here is non-zero. Only the statistical value over bar, right? So then we say, so this kind of flows exist where you have a statistical stationary flow as well as a statistical homogeneous in a particular direction or more than one direction. Is this clear? Fine. So now apart from this statistics, we are going to apply this knowledge to a particular flow, the same plane coed flow, and revisit the Reynolds stress equation. Okay, so let's just look at this particular flow now. Plane turbulent coed flow. I am just taking this as an example. So if I take this particular example, I am going to consider what is called fully developed stage. Okay, so consider the flow is fully developed. And you have also make sure that the flow is statistically stationary and all these things. Okay, so that you have done. So in this particular case now, so what will happen when all these conditions are there? I have checked for statistical stationary, right? So statistical stationarity has achieved. So flow has achieved statistical stationarity. So here my dou by dou t of all the quantities, statistical quantities are 0 in this flow now. And then I also have inhomogeneity only in the one direction, right? So if I take, instead of this xyz direction, if I simply take this problem as in the coordinates that we are using, so we have x1, x2 and x3 is the out of plane component, right? x3 is the out of plane component, this is the fixed wall and this is the moving wall. Not u infinity, let's call it some u reference velocity. Okay, so if I have this, then here we have homogeneity along homogeneous along x1 comma x3, which implies dou by dou x1 of any statistical quantity is 0, dou by dou x3 of any statistical quantity is also 0. I will also show the data later from my own direct numerical simulation, but let us consider that it has come to a stationary state, statistical stationary state, and it is also statistically homogeneous along x1 and x3. And I also mentioned that the flow is fully developed. When the flow is fully developed, turbulent plane fluid flow, we also get what is that as the second and the third velocity components. When this happens, your u2 bar equal to u3 bar equal to 0. In a laminar plane fluid flow, that is easier to see. One can prove this analytically. In a turbulent fluid flow also, I will show you the data. u2 bar will be equal to u3 bar equal to 0. Only the u1 bar exists. Okay, so that will look like this. It will have a profile like this. This will be your u1 bar. Not linear as it should have been if the flow was laminar, right? So a turbulent plane fluid flow will have u1 bar looking like this. So I have this condition, right? So with this we will go back to our equations and see what happens to each of the term. Okay.